In my previous video, I've talked about the economic incentives behind in-space manufacturing and space tourism. But at the end of it, there's still one question left. There's still no good reason to go beyond Earth orbits for the foreseeable future. And as I said in the previous video, something that doesn't have clear economic benefits will never get developed. That said, I did briefly hinted that the answer to this lies in the raw materials that we will need for our space industries. So in today's video, I'll discuss what it is about these materials that will drive investors to the moon and beyond. Alright, before starting today's discussion, there's something that I need to make it very clear. Everything that I'll be talking about today, all after a robust in-space manufacturing industry has already been established, which will be at least a few decades from now. If you don't know why we would ever do such thing, or what are the implications of that, then I would highly recommend you go watch my previous video first, which will be somewhere around here. Because otherwise, this video won't make much sense to you. In that period of time, the tourism industry and agencies like NASA and the CNSA would have definitely come to the moon well before any of this happened. So keep those in mind because they will be important in this video. Now back to all the materials that will need to be transported to the in-space manufacturing facilities. Believe it or not, the moon has a lot of the same resources as we have here on Earth. After all, the moon was part of the Earth that got ripped off 4.5 billion years ago. And transporting those materials to Earth orbits will take a lot less fuel than comparing to transporting them from the surface of the Earth. Which I'll prove it to you right now. This is the rocket equation, at least the simplified version of it. But for the purpose of this video, it is still a good enough approximation to prove my point. Now if we manipulate them a bit to get MO, the initial mass of the rocket, as a function of delta V, the change in velocity that's required, will have this function. And given that every other terms are fixed, in the long term the function will tend to this. By approximating MO to be the fuel mass, as over 90% of the current rocket mass is fuel, we can see that approximately the amount of fuel needed will be proportional to e to the power of delta V. Now if we assume that e is approximately equal to 3, then if we double the required delta V, we would not double or triple or even quadruple the amount of fuel needed, but would increase the fuel needed by 9 times. 27 times if we triple the required delta V, and 81 times by the time we quadruple our delta V. Now I can show you right now the calculation for the delta V required to get from either the moon or Earth to these orbits, using fancy tools like pencil and papers. But for simplicity's sake, I have the already calculated delta V map to different orbits, trajectory, and destination here on the screen right now. On here, on this graph, every dot represents an orbit, trajectory, or destination, and every line represents a path from one dot to another, with the delta V required to go in either directions. Low Earth orbit, LEO, is the lowest possible orbit you can be in, and it's the orbit that takes the least amount of delta V to get from Earth, which is between 9.3 and 10 kilometers per second. All while taking the highest amount of delta V to get to from the moon. Now if we take this path to go from the moon surface to lunar orbit to Earth C3 equals 0 orbit, also known as escape orbit, to geostationary transfer orbit GTO, and then to LEO, it would take us a total of 5.5 kilometers per second of delta V, which is just over half to less than 2/3 the delta V required to get from Earth to LEO. And please don't tell me about the shortest path, quickest path, or anything. They are raw materials. Time doesn't matter. All that matters is minimizing the cost of transportation, which in this case is minimizing the delta V required. So you can see that there's a huge difference in delta V required even in the most favorable condition for Earth. And because of the tyranny of the rocket equation as shown above, that will translate to an exponentially larger difference in fuel requirement when transporting stuff from the moon to Earth orbits, when compared to transporting those same stuff from the Earth to those same orbits. But that's not all to it. If we take a look back at our manipulated rocket equation above, then if we take a look at the relationship between MO and VE, engine exhaust velocity, in the long term, we can see that they would be like this. Then making all the same approximation, we'll see that if we double the engine exhaust velocity, we reduce the propellant mass by almost half. Now the scaling of this relationship is not as impressive as the previous one, but it's still an improvement. And the reason why I bring this up is because since we're traveling through deep space, where there's no environment and human population, we might be able to use more exotic type of propulsion engine. Things like thermonuclear propulsion technology. It's a technology that had been proven back during the Apollo era through the NOVA program, and the design tested and demonstrated in the program can roughly double the exhaust velocity of the engine. But there are other designs of that same type of engine that can bring that number up to over 14 times even the most efficient chemical engine right now. So this engine can effectively cut the fuel needed by 1/2 to 2/3. The reason why these engines are not used here on Earth, but can be used to travel through deep space is because, well, they spew out radioactive exhaust everywhere. But since space is already extremely irradiated, a little more won't hurt anyone. But the advantages of these engines aren't just in that they save fuel, but also in the fact that they can use anything that can be vaporized at the operating temperature of the nuclear core, which is a lot of things that can be found locally on these space celestial bodies, reducing the cost of having to bring fuel with you from Earth and using specialized fuel. Okay, so I've just proven to you that shipping materials from the moon is cheaper. But what materials do we even have there, and can we even extract them economically at scale? Well, several missions have confirmed that the lunar regolith, which is the top 5 to 10 meters of soil on the moon, contains a large amount of metals and minerals. And according to the sample brought back to Earth during the Apollo 12 mission, the moon regolith, in terms of weight, is 42% oxygen, 20% silicon, 12% iron, 7.5% calcium, 7% aluminum, 6% magnesium, 2% titanium, and 0.5% sodium. So, just by scooping up some moon dust, you effectively already have many of the important elements, including metals that are vital to the modern industry. There are also other trace elements, which, although make up a fraction of a percent of the moon composition, can still be extracted at scale, notably nickel, cobalt, manganese, rare earth elements, lithium, copper, phosphorus, thorium, and potassium, along with volatiles including but not limited to methane, ammonia, methanol, carbonyl sulfide, and hydrogen cyanide. In particular, water, although mundane, is of particular interest to us because of its involvement in many industrial processes and machineries, and its importance in supporting human life in space. The moon is also believed to have had active geological processes in the past that facilitated the transportation and accumulation of concentrated mineral deposits, but those will need more scouting and exploration to confirm their existence, locations, and quantities. And I guess that you already know about the value that these resources bring about to our modern industries, so I'll skip over the explanation for that. As for how we're going to excavate and extract those resources from the lunar regolith, while doing the research for this video, I found this channel, Anthrofuturism, who has done a fantastic job at explaining it over a series of videos appearing on the screen right now, and will be linked below in the description of this video. But to summarize, the TLDR is that we can excavate, transport, and refine lunar regolith with relatively simple machineries and infrastructures made almost entirely from resources on site, which is a process known as In-Situ Resource Utilization, ISRU, and with minimal shipments of advanced electronics from Earth. Basically building an entirely on-site, vertically integrated resources supply network. What that basically means is after some minimal amount of infrastructure to mine and refine regolith, as well as minimum basic manufacturing capabilities is set up on the moon, it's relatively easy and cheap to continue to expand and operate the facilities. You do not need to buy and import most of the materials from Earth because they are able to be made from the moon regolith, and only a minimal amount of shipments for advanced electronics is required. And by that, I only mean the processors. The circuit board can be made on the moon as well. You also do not need to pay for energy because the sun is free, and we can make photovoltaic out of moon regolith to generate electricity, or build solar furnace using the abundantly available aluminum to harvest heat energy. Spare parts for maintenance will similarly be made out of moon material using the free energy from the sun. As for labor costs to operate the mine, indeed there's no way around this. But look at this. Look at how all those heavy vehicles are teleoperated. Then look at how the robotics industry has been moving in the past 2 decades. Remember what I said at the beginning of the video. This is all after a robust in-space manufacturing industry is established. So not only will there be plenty of time for new advancements in the robotic industry to happen, but in-space manufacturing itself is a highly automated industry and will also contribute significantly to the robotic capabilities we will have. Large-scale mining operation on the moon does not necessarily require a lot of human workers on site. Given that round-trip signals between Moon and Earth take less than 3 seconds, most machineries and robots can be teleoperated and don't necessarily need advanced AI capability either. Only a small rapid reaction team is needed to stay on the moon to fix things up if something does go wrong. Even then, a fleet of humanoid and other types of robots can be used to do the regular maintenance and fix simple problems that can be teleoperated from Earth as well. And so it doesn't seem that the labor cost will be significantly higher than mining operation here on Earth. Unless, of course, you want to disregard all human rights, safety and health standards, and compare them to exploited workers working in artisanal mines in third world countries. In the lack of interaction with a free market system, the cost of setting up, operating and expanding a mining facility on the moon is essentially the sum of the R&D cost for developing the required technologies, cost of transportation, cost of raw materials, cost of energy, and cost of labor. And other than the R&D cost, as laid out above, cost of energy is non-existent. Cost of raw materials is also non-existent except for that initial minimum amount of machineries and infrastructures required to start mining, refining, and manufacturing from moon regolith, which is usually called initial capital expenditures, and a minuscule amount of advanced electronics. Cost of transportation, again, is non-existent except for the transportation of things mentioned in the cost of raw materials above. And the cost of labor, which as mentioned earlier, is not going to be significantly higher than operating the same mine back here on Earth. So all that's left to sort out to assess the economic viability of developing a mining industry on the moon is what are the R&D required to develop mining, refining, and manufacturing capabilities on the moon, and what's the initial capital expenditure required to get that minimum amount of initial equipment up there. Fortunately, the former is already being carried out by private corporations like Blue Origin through its Blue Alchemist program and Lunar Resources. There's plenty of time till then to spread out the cost. The funding for this will not dry up anytime soon due to the fact that there are many deep pocket parties that are interested in these technologies, including Jeff Bezos, and nations like the US and China, which are seeking to establish permanent presence on the moon. Not to mention the moon tourism industry that will surely be there well before any of this happens. And in any case, does not require too many new technologies that haven't been tested before either, just that they haven't been used together and used in space before. We employ extremely complex mining, refining, and manufacturing techniques here on Earth, because we can afford the complexity. Energy here is expensive, and materials are limited. But on the moon, it's exactly the opposite. We have lots of energy and materials, but because we're starting from scratch there, we can't afford much complexity. And as it turns out, if you dump in enough energy, and don't scam of waste or inefficiency, you can refine and manufacture anything, even from regolith, without much complexity. Development of one-size-fits-all manufacturing techniques like 3D printing and CNC machining should also help in achieving that goal. As for upfront capital expenditure cost, our objective is to ship the minimum amount of equipment required to get the refining and manufacturing process started on the moon to build ISRU facilities. And for that, the major machineries that we'll need are one bulldozer, one loader, one dump truck, one self-contained micronuclear reactor that output at least a few megawatts of electricity, a solar furnace, which is just a lot of reflectors to focus light onto one spot, heating things to upward of 5,500 Kelvin, a reactor to process our regolith, whether it is through molten magma electrolysis, direct sublimation, or other means of refining regolith, a 3D printer, and a CNC machine. The bulldozer, loader, and dump truck can all fit into one starship. We don't need the biggest mining equipment on the moon. We can even have several smaller ones instead of one big one to have redundancy. This is all because, based on my calculation, our production rate will certainly be limited by the amount of energy we have well before we hit the limit of how much regolith we can scoop up from the ground. The cost of those mining equipments are probably non-existent when compared to all other costs, because we aren't designing anything from the ground up here. Next, our solar furnace, the most likely limiting factor to our production rate, could probably be shipped on the same ship as some other materials. But to be extra generous, let's dedicate an entire ship to it. Now, before you're asking how we're going to fit a solar furnace big enough to process moon regolith onto one ship, you should take a look at this proposal for the Lunar Crater Radio Telescope and light cells. The former used cleverly engineered carbon fiber cable to create the required shape and support needed to deploy a 350-meter diameter radio telescope, all deployable from a single lander the size of the Apollo lunar lander, while the later used extremely thin and lightweight reflective sheets to essentially sail using only light. We can combine the two to create something similar for a solar furnace. And because we aren't constrained to only a few tons and the technologies we have at the moment like NASA, we could scale it up to, let's say, the original proposal, which is a 1 kilometer diameter parabolic reflector, and bring with us supporting towers and robots to help simplify the deployment process. That gigantic of a solar furnace, when deployed, can concentrate enough sunlight to vaporize 24,000 tons of regolith. That's enough regolith to fill up a Panamax cargo ship in just over 2 days. NASA projected the cost of the Lunar Crater Radio Telescope to be at least $2.4 billion. But again, we're not NASA. We're not trying to build any of this today when the technologies are not ready, launch cost is still high, and no human presence on the moon is established. In 20 to 30 years time, however, I would say that 500 million is a good conservative estimation for something like this. We would also need a micronuclear reactor for electrical energy supply. Companies claim they can produce micronuclear reactors that are fully self-contained in a single shipping container at sub-$100 million cost within a few decades. But to be extra conservative, let's say that we'll have to design our own reactor and leave an entire Starship upper stage on the moon to house that. I'll put the price tag for this at $1 billion for a 20 megawatt reactor on the moon. Finally, the last major equipment we need to ship to the moon are the reactor to process the regolith, using whichever method you prefer, an industrial 3D printer, and CNC machine for multifunction manufacturing, all of which can fit inside another Starship. So that's 4 ships for the major machineries. I'll make it 10 to account for other robots, casts, molds, and other equipment necessary to manufacture stuffs. That will total the transportation cost to be $200 to $400 million, not to mention more advanced launching vehicles we might have by then. Adding all up, the major cost will amount to $2 billion, and accounting for other small costs that wasn't accounted for. Let's just be extra conservative again and round that up to $5 billion. I'll say that a cost of $5 or even $10 billion for initial capital expenditure is a reasonable investment that companies will be willing to pay, given that that will open the door to essentially unlimited reserves of dozens of different minerals, many of which are critical resources here on Earth. Those are economic incentives that will motivate investors to go and invest in industrializing the moon. Once we have a matured enough mining industry on the moon, other manufacturing industries in Earth's orbits will gradually migrate to moon orbits as well, to form an industrial complex on and around the moon. This is because the more we process the raw materials and the closer it is to the final product, the more waste we'll avoid and the less fuel and energy will be needed to send them back to Earth. Earlier, I mentioned that energy and raw materials are free, and so we can afford to use them in a less efficient way when starting out to reduce complexity. But that doesn't mean that we shouldn't eventually strive to be more efficient, as the less materials and energy we waste, the more products we can produce, increasing our profit margins. Following the resource extracting and manufacturing industries, tourism and its supporting industries, along with other servicing industries that provide services to improve the quality of life of the people living and working in this new industrial complex might follow suit, potentially forming a full-fledged economy in space, providing new opportunities for people like back in the 16 and 1700s. And once you have mastered all these technologies on the moon, you may want to build ISRU spacecraft to go harvest resources from near-Earth asteroids as well, using all the same techniques we have discussed earlier, because all the math about delta V advantages for them will still hold. And there are asteroids that hold trillions of dollars worth of valuable materials or holds essential elements for modern industry that just aren't common on the moon like carbon. This, along with my previous video, is my vision for how space development will ultimately play out. And the reason why I don't really buy into the arguments that space is just not economically viable, like most people usually say. Economic explain. Hopefully, these two videos of mine have done a good enough job at putting up an argument for the economics of space development, so that the next time someone tries to tell you space is just a waste of money and it can never be profitable, you can show them this video and prove them otherwise. Thank you very much. My name is Tai Yum, and this is I Have a Dream. Alright, time to address some details that I brushed over in the video. First is the rocket equation. It doesn't behave exactly the way that I described earlier. Yes, MO is proportional to e to the power of delta V over VE. But since delta V over VE is acting as the exponent of e, any changes to one will affect how the whole function will act with respect to the other variable. And so the accurate way to analyze how MO will grow or shrink is to not ignore the other variable and analyze the two separately like I did, but to analyze them together in a two-variable function of e to the power of delta V over VE, and then wrap them in three-dimension space like this. Well, I don't have the tools to build myself a 3D model for this, so I'm using decimals, and in here, x is the delta V, y is VE, and z is the initial mass for a payload of 1 unit mass. You can see that the graph of this function is a two-dimensional surface in a three-dimensional space, where every combination of x and y values has a corresponding z output. If this is too hard to make sense of, you can think of it as a family of graph of MO as a function of delta V with different values of VE. The graph still behaves roughly the same way as I described earlier in my video, but as VE gets larger and larger, the graph gets squished more and more downward. Also, an exponential function doesn't get multiplied by a fixed amount if the input is multiplied by a fixed amount either. What I mean by this is, say you have 10 to the power of 1. You can double the exponent to 2. You go from 10 to 100, a 10-fold increase. But if you continue to double the exponents to 4, you now go from 100 to 10,000, a 100-fold increase. Why that is because of a property of exponent where if you have a starting exponent, then you multiply that by another number, it is equivalent to your original base raised to your starting exponent, or raised to the new number. So basically, your original base raised to the starting exponent is now acting as your new base, which is much larger and therefore grow much faster. As a result, the simple ratio that I gave earlier is not the complete story and is entirely dependent upon the starting conditions. The simplified arguments that I gave about the rocket equation is for illustrative purpose only. They may not be 100% accurate, but they do get the main points across. Hence why I'm making this part right now to add the necessary corrections. Also, I'm sorry that I'm not 3 blue 1 brown, so that's the best that I can explain and visualize the math. Next, we have the ease and prioritization of ISRU manufacturing for different things. Earlier, I talked about how we can manufacture almost everything locally on the moon if we dump enough energy in. That said, not everything can be manufactured locally when starting out, at least not without increasing our initial capital expenditures to an unreasonable amount. Parts that only require mechanical, electrical, or thermal processes to be made, like structural and electrical components of machines and systems, are probably gonna be the easiest to be made in situ. Whereas parts that require chemical synthesis or wet chemistry to be made, like chemical batteries, are gonna be more difficult and should definitely be avoided when starting out. What I'm proposing here is that machines on the moon should be designed to maximize the use of the former while minimizing the latter. For example, in the case of energy storage, it's better that we replace the batteries with thermal or mechanical energy storage solutions instead, like for example liquid air or compressed air batteries, or molten salt storage tank coupled with radiators. They'll be more heavy and bulky, but those things aren't such a big concern on the moon, and they'll help us keep the cost down until production lines for batteries can be established. Also, on the note of designing machines and systems to be manufactured on the moon, Anthrofuturism did talk about using cables and rope system. They're fine, but in my opinion, we should use more modern electromechanical actuators for that job. They are stronger, require less maintenance, while being just as easy to be manufactured. Or even electromagnetic actuators, which are not as strong but still stronger than ropes and pulleys and require even less maintenance. I should also mention that it is possible to synthesize hydrocarbons from carbon dioxide and water on the moon, and we will want to do that given the usefulness of products made from them. But I do agree that using them for hydraulic systems is definitely not a smart choice. So I cover things that should be manufactured in situ immediately when starting out, and things that should be avoided until production lines are established already. But there are also things that should probably never be manufactured on the moon. For example, processors. By the time we can set up a mine on the moon, lithography and other required technologies to manufacture processors would have had over a century head start here on Earth already. Trying to catch up with that will definitely be very costly and time consuming. That's not to mention all the specialized chemical used in the manufacturing process that took centuries to develop and require the entire global supply chain to supply. I'm not saying it is impossible to do, just that there's no economic reasons to do it. Each processor costs in the tens to tens of thousands of dollars to manufacture. Whatever the transportation cost to the moon is not going to even make a dent in that cost. So better just import them from Earth, or from the orbital manufacturing industries. My second last point is about the ease of extracting resources. Probably by now, a few of you would have raised the point that if resources can be extracted by such primitive machines and refined by just dumping in a lot of energy and materials without thinking about waste like I proposed, then why do the mining industries on Earth require such sophisticated machines and processes to extract and refine their products? The first reason is like Afrofuturism has mentioned in his video. The Earth is covered with organic materials, whereas the Moon is covered with regolith. But I think the more important point is that we actually used to extract and refine resources using primitive technologies, not so different from the one I described in this video. Humans started large-scale mining operation back in the 1800s. Mechanized tools were just introduced not long before that. and standardized production line were not a thing up till the early 20th century. Back then, deposits of many resources are also located right on the surface, just like on the moon. And so we started mining them using human labors, primitive tools, and refined them using very primitive processes. We got more sophisticated and efficient over the past 2 centuries because we want to scale up our operations, and on Earth, that's the only way to do it. But on the moon, there are other ways to achieve the same result. We could just scale up the size of our primitive machines, for example. The size of every machine is limited by the square cube law, which states that the weight of any object will roll much faster than the strength of said object. Therefore, at some point, they won't be able to support their own weight anymore. The thing is that on the moon, everything weighs 1/6 of that of Earth, and so we should be able to get our machines much bigger before hitting that limit. Another example is, as I said above, we can just expend more energy and resources to compensate for our lower efficiency. It is not that we can't do that here on Earth, but probably no one will approve setting up a 1 kilometer parabolic mirror next to a mining site to refine their metals ores, when the mine itself is already taking up valuable space and damaging enough to the environment around it. And back then, we probably didn't have the space and capabilities, and the Earth's gravity probably would not allow for such thing to be built anyway. So, it's not that we've never done anything this way. We once did. And now, we're just taking that and scale up to meet our criteria. Finally, I want to address the point that I use vacuum pyrolysis in my math of how much resources we can extract, and that's molten magma electrolysis. You see, molten magma electrolysis requires 50 megawatt hour per ton of regolith refined. That means with our measly 20 megawatt nuclear reactor, we can only process less than 10 tons of regolith per day. That's not enough to do anything, so we'll need to change our mission design. Forget 20 megawatt. We need to modify our Starship to each carry a 200 megawatt reactor. Luckily, there's within range of small modular reactors, and these guys have higher level of technology readiness than our micronuclear reactor, as well as still being able to fit everything into one Starship. So hopefully, they won't exceed our budget overrun margins that I laid out above. This would calculate out to 100 tons of regolith per day per ship, roughly 36,000 tons of regolith per year. This is workable, but ideally, we would want more than one ship. If anyone is wondering, the solar furnace we had was equivalent to just over 2 nuclear reactors. But we would need to bring additional generators and radiators to make it generate electricity, so any benefits of repurposing the furnace will be negated. And even then, we will need to focus even more on ISRU manufacturing than the previous scenario. Why? Because we need to expand our operation to meet the demands back in orbit and back on Earth, and generate large and quick enough returns to justify the original astronomical investments. 100,000 tons per year is still nothing, and keep scaling up our production this way is not sustainable. It is here that I also want to address this video of Afrofuturism as well. No, we should not just import our vehicles from Earth. We will need to manufacture other machines and systems anyway. And if we already have the capabilities to do that, it should not be that hard to manufacture the vehicles as well, especially given the fully mechanical and electrical design that I laid out earlier, and that we don't need that many vehicles. Unless, of course, you look at my arguments and say, hey, it looks like we can refine a lot of regolith with just our imported systems. Why not just import everything? In such case, I'll just say, why not importing them to the moon at all and use them here on Earth instead? With the cost of keeping one such mine operation on the moon for 4 decades, I can easily open 40 to 80 more mines here on Earth, operating for the same period of time, each rivaling the production rate of the moon mine. Again, not that many people are interested in space or even technological advancements in general. And from the perspective of a cold, heartless economist, the former is clearly a worse investment than the latter, and the products of the latter is clearly more competitive in the markets than the former. Okay, so that's all for the added details. If you still have any counter arguments, leave them in the comments section down below, and I'll answer them in the after credits of my next video. I've decided that from now on, the after credits section will be where I address details that are too long and distracted from the main argument, and announcing channel updates. So here are the updates of this video. Next video will be the final video of this space series, at least for now. The video will address what's missing in my arguments for the economics of space industrialization. How will any of this benefit the lives of the everyday people? And I mean specific benefits to specific people, not just the general. Yeah, it will benefit people indirectly. After that, there will be a special video for the upcoming Avatar Fire and Ash movie, which will talk about why the human world in Avatar can never be such a dystopian place given the technologies they have. And then after that, a series on the future of energy, energy storage, energy production, and energy transmission. That's it. Thank you for watching. If you find this video helpful or interested in any way, you can help me by leaving a like, comment, or share it to someone who you know will like the video. And see you in my next video.